Good morning, students. Once again, you all welcome in my YouTube channel. I am Sunil Sangle. Today we are going to discuss the new concept under the unit number 5, which is based on digital to analog converter and analog to digital converter. The topic is binary weighted resistor DAC. Already we discussed in a previous lecture what exactly mean by digital to analog conversion, and what is the need of to convert digital to analog and vice versa, analog to digital. So digital to analog conversion, there are different types of DAC, that is digital to analog conversion. First one is binary weighted DAC, another one is R to R ladder. So today we are going to discuss in very detail what exactly the binary weighted DAC and how it works with the examples. So binary weighted resistor DAC is one of the way to achieve the digital to analog conversion is to use a summing amplifier. By using the different resistors, it can be used to convert digital to analog. This approach is not satisfactory for the large number of bits because of it required too much precision in the summing registers. So this drawback is overcome in the R to R network ladder. Later on we'll see what exactly R to R ladder DAC, but before that we'll see in detail binary weighted resistor DAC. So this is the basic diagram for the R to R ladder. Here the binary inputs or digital inputs are given through the different register values. The register value for the MSB is less than the highest register value for the LSB. So here the LSB is highest register value, and that all the inputs are given to this amplifier by the connecting the reference voltage as well as reference register, and finally we'll get the analog output. We'll see how exactly the analog output will get. So here the B1, B2, B3 up to Bn, these are the binary inputs are given, and the digital control inputs are connected through this. Suppose you are giving the input 0, that time this B1, B2, B3, a particular bit will connect to the that voltage 0, and when you are providing the voltage binary input 1, that time it will be connected to voltage 1. So like this, ultimately we will get the output V out, that is the analog output. Expression for analog output voltage, how exactly we will get that analog output. So I output means current input I is equal to I1 plus I2 plus up to IN. So we know that I is equal to V upon R as per the Ohm's law. So we'll put that V reference, voltage reference, and for the each and every binary digit, that is a whole register value 2R, 2 raised to 2R, 2 raised to NR up to all register value is given here for the all the decimal binary digit. So ultimately we'll get the output current is equal to VR upon R by taking the all commons value output V upon R, and then putting that particular equation D1, this is a decimal binary digit 2 raised to minus 1 plus digital input 2 raised to 2 minus 2 plus like this up to dn 2 raised to minus n. Then output voltage V out is given below. Suppose already we know V is equal to IR, so putting that the current as well as reference register here, so V out is equal to I0 I out into RF After putting that equation into the above equation, we'll get that equation. Then when we are considering the scaling factor K, but suppose K is equal to RF upon R, and VFS, that is the full scale voltage, is equal to VR, then putting that all values into the above equation, we'll get the voltage output is equal to VR in bracket D1 2 raised to minus 1 plus D2 2 raised to minus 2 up to the Dn 2 raised to minus n. This is the final equation for obtaining the analog voltage. Example, for the calculating the analog output voltage for the 4-bit DAC, if the digital input is 1101, and for assuming that voltage reference voltage is equal to 10 volt and common factor or scaling factor K is equal to 1. So already we know that output voltage is equal to KVR, and D1 2 raised to minus 1 plus D2 2 raised to minus 3 up to this. Putting that all values, we have the 4-bit DAC input 1101. So here putting that value 1 here, and for the 0 we are nothing is there, so putting that value is 0. So after that calculating, putting that all values, will get the 0.8125 and multiplying with the 10, will get the final answer 8.125. This is the output voltage for the digital input 1101. This is analog output. So here this is the one of the example for the weighted sum DAC. Thank you for watching.